Hello everyone and welcome back to PC Retro Programmer. In the past couple of videos we've been taking a look at how to draw a quadrant of an ellipse using the algorithm that you see on the left of the screen that I developed, and we've implemented this in 8088 assembly language and you can see the result on the screen. Now the only thing standing between us in drawing a complete ellipse is that we need to reflect this about the horizontal and vertical axes. If we reflect this about the horizontal axis, then we'll end up with the entire right-hand half of the ellipse, and if we reflect that about the vertical axis, then we'll end up with a complete ellipse. And so that's what we're going to do in today's video. Now, I mentioned in the previous video that it's not going to be practical to draw the points on the right-hand side and the left-hand side of the ellipse at the same time with the same code. And the reason for that has to do with how pixels are laid out in video RAM. It's just not true that a pixel on the right hand side of the ellipse, which is say in the rightmost bits of byte in video RAM, is reflected by a pixel on the other side of the ellipse that is in the leftmost bits of the byte in video RAM. It really depends where the center of the ellipse is, and the two could really be in any position in the byte. And on one side of the ellipse we might be decrementing the byte by 1, in the other side of the ellipse we might still be just shifting the bits within the byte. And so the same piece of code isn't going to take care of both cases at the same time. So the only way we could actually handle this is by duplicating the set of registers that we're using to keep track of pixel drawing. And at the moment we're completely out of registers. So that's really not going to be practical. Now I'll say a little bit more about this at the end of today's video, but the main thing we're going to look at today, which is of interest, is to reflect about the horizontal axis. Now this is possible to keep track of with very little additional information. It turns out that it really is the case that a pixel on the bottom of the ellipse, when reflected, uses exactly the same information except for where it's being written in video RAM. The only thing that's different between the two is the offset. And so we can keep track of the reflected pixels simply by keeping track of this additional reflected offset. And this is only an additional register. We are out of registers and we're going to make up for that by using a memory variable instead. But all the other code is basically going to remain the same. It's only this small additional piece of information that we need to make use of. So let's take a look at the code for doing exactly this. This is the new code here. It's ellipse3.asm if you're following along at home. There's a link in the description to my repository if you want to find this code. It's basically the same as ellipse2.asm that we saw in the previous video with a few minor changes. So one of those changes is this memory variable that I was talking about. As I said, we've run out of registers, so we need to store one additional piece of information in memory. And that means that we're going to put it in the data segment. That's what this .data stands for here. And we're declaring a variable called ellipse diff in our data segment. This DW here means to declare a word. And so basically it means to set aside a word of space in the data segment for this variable ellipse diff. And we'll start it off with the value 0, although that's not particularly important. We're going to need to set this value to 0 at the start of the algorithm every time it's run, and I'll explain why in a moment. This variable exists in the data segment, which basically corresponds to the DS register in the CPU. And you might wonder, well, how do I access a variable in the data segment? Well, you don't actually need to write DS anywhere explicitly for the most part, and that's because almost every instruction that accesses memory assumes that you're using the data segment. The main exceptions to that would be if you were accessing the stack, say with the stack pointer. That certainly assumes that you're using the stack segment or the SS register. But for everything else, the DS register is assumed. So let's take a look in our code where we're actually using this memory variable ellipse diff. So I'll just scroll past some of this setup code here. Here's the first place. I basically just set it to 0 when the algorithm starts. Now I need to do this because this algorithm might have been run multiple times, and there could be any value in this ellipse diff by now. So I actually need to explicitly set it to 0, and this is what the code looks like. I move the value 0 into my ellipse diff variable, and I'm just telling the assembler here that this is a word pointer, and this is probably not actually necessary here simply because ellipse diff is declared to be a word in size. It might actually figure this out for itself, but it's just a habit of mine to make sure we annotate whether we mean a byte or a word or whatever. And that's the way that you write it. So let's scroll down to where we actually use this memory variable in the code itself. So we'll skip right past all the setup code and down to where the main loop starts. And the first thing we do in the main loop is to draw a pixel. And that's what all this code is for. This is the STOSB instruction for writing the byte into video RAM, and that actually draws our pixel. And of course I decrement the DI register here, our offset, because STOSB automatically increments the offset, and I want to undo that. And now in order to switch over to the offset for our reflected pixel, all that's going to be necessary is to subtract this ellipse diff value. So I'm actually not going to store the alternative offset in this memory variable. I'm just going to store the difference between the two offsets in the memory variable. So every time I change lines in my code here, I'm also going to need to update this difference so that it has the correct difference between the scan line that I'm on and the reflected scan line. So that's how it will work, and now after I've subtracted this difference, I've now got the reflected offset in my DI register, and I can go ahead and draw exactly the same pixel again, just in that different location. And you can see that this code is identical to the code above. So we use the same pixel drawing code and the same values, just writing it to a different offset in this DI register. Now, of course, I don't need to decrement DI down here. I only did that because I needed to get DI back to the value it would have been before I drew a pixel, because that's what I'm going to need when I do this code here. Okay, so that's all there is to it really. Now the only other thing that I'm going to need to do here is to alter the ellipse diff value every time I change scanline in my code. So let's scroll down to where that happens. So here's an example here. So I'm incrementing my scanline by 1 here. I'm changing the y coordinate by 1. And I'm basically going to have to change the ellipse diff value to reflect that. And the way that I'm doing this is to add 80 bytes to this value. Now 80 bytes is one scanline, and you might ask, well, why is it only 80 bytes? Why is it not 160 bytes? After all, the point on the bottom of the ellipse has moved down one scanline, and the point on the top of the ellipse has moved up one scanline. Surely this is a difference of 2 scanlines, and that would be 160 bytes. But there's a little bit of a wrinkle here, and that is the way that scanlines are stored in video RAM. Remember that all the even scanlines are stored in one half of video RAM, and all the odd scanlines are stored in the other half of video RAM. So actually, we're always either switching between an odd scanline and another odd scanline when we do the reflection, or we're switching between an even scanline and an even scanline. And the difference in bytes between these is only 80 bytes instead of 160. And so that's why the value 80 is used here instead. Now the other thing that I've done here is to add this ellipse diff value back on the DI register. Remember that in our code above we actually subtracted this value from DI. So in order to get it back to its original value, we add it back on again down here. And that's pretty much all there is to it. You can go through the rest of the code, and there are a few other locations where we change our Y value, and in those cases we also have to change our ellipse diff value by 80. So here's an example here, and that's really all there is to this code. So let's just run this and see the result. Well, this is what it looks like when we run this, and you can see we get the entire right-hand half of the ellipse. So the only thing remaining for us now is to draw the left-hand side, and as I said, the way that I'm going to do this is just to duplicate the code, but everywhere that I would have moved left by 1 pixel, I'll move right by 1 pixel instead. And of course I'll start at the leftmost point of the ellipse instead of the rightmost point of the ellipse. But otherwise it's exactly the same code, and so I just end up running pretty much exactly the same thing twice. Just one of them moves left while the other one moves right. Now there is one little wrinkle, and that is the STOSB instruction. Remember that this automatically increments the offset by 1 every time it's run, and so I do need to make a little adjustment for that, but I'm sure that you can imagine how to handle this. It's pretty straightforward. In fact, there's actually an automatic way to handle this. We can actually change something called the direction flag in the CPU flag register. So if you change the direction flag, then instead of STOSB incrementing, it will decrement instead. So that's an automatic way that you can handle this. But I'm not going to bother showing the code. There's nothing really interesting about it. It's just the same code duplicated. It's in ellipse4.asm if you want to look at it in the repository. So let's run that and see what the complete ellipse looks like. And at last, here is the result. Now stay tuned, a little bit later in the video we'll use this code for drawing circles. That's ellipses with a ratio of 6:5 because of the fact that the pixels are not quite square. And I'll also animate this and move it about a bit, just so that we've got something interesting to look at. But the other thing you might notice is that this ellipse is a little bit jagged, and there are a couple of points where there seem to be some little bumps. Now, there's nothing wrong with the algorithm here. It's doing the correct thing. We call these the jaggies, and there's not very much we can do to get rid of these. These are just a result of the fact that we're using discrete pixels to approximate a smooth object. An ellipse is perfectly smooth, but we have to pick the pixels that are nearest to the ellipse. And sometimes the pixels that are nearest are on one side of the ellipse, and then all of a sudden the nearest pixel that comes next is actually on the other side of the ellipse, so we get this kind of jump effect. So there's absolutely nothing we can do to eliminate this. It's just a result of the fact that the pixels are large enough that we can actually see them. But I still think the result looks relatively pleasing. Now, I said earlier in the video that drawing the left-hand side of the ellipse at the same time as the right-hand side is going to be pretty impractical. But I've had a little bit of a think about that, and it might actually be possible. Now, we are still out of registers, so we're definitely going to have to add some memory variables if we want to do this. But we really just need to duplicate the information that we're storing for drawing pixels. All the rest of the code could remain the same. And the only information that we're storing at the moment is a mask byte and the offset. So that would just mean that we'd need one 16-bit value in memory and one 8-bit value in memory for the mask, in addition to what we already have. It doesn't seem like that much, actually. And the saving would be that all the computations that we've done for the right-hand side of the ellipse wouldn't have to be done again for the left-hand side. And it might actually be faster. So in the next video, I'm going to try that out, and I'm actually going to time the two and see whether or not it is actually possible to get a faster result by keeping track of this additional information in memory registers. So stay tuned for that video. But for now, what I want to do is finally switch over to a ratio of 6:5 so that we can see what a circle looks like, and then we're going to move it around the screen. Now before I do that, I've got one question for you. Supposing we do the optimization that I just mentioned, where we end up drawing all 4 reflected points at the same time with the same code. That's going to be pretty fast, right? Is that the fastest we could go to draw an ellipse? Well, it turns out that it's not. There are actually additional improvements we could make. So one of those improvements would be that we could have special code for very small ellipses. If the ellipses are small enough, then all the values would actually fit in 16-bit registers, and we wouldn't need to use any of these 24-bit tricks. And so we could just have the code automatically switch from 24 bits to 16 bits and just have 2 versions of the code, and this would enable it to draw smaller ellipses much faster. It's probably not an optimization that you would bother actually doing in practice, since it's also going to basically double the length of the code for drawing ellipses. But if you really cared about performance, you might do that. The other question I'm going to ask is, can we do any better if we're drawing circles? And by circles here I mean with a ratio of 6:5 so that they actually look circular on the screen. And initially you might say, well, of course not. I mean, we need the full standard ellipse code for drawing these. But it turns out there's actually a trick that we can use to get circles and have a specialized code for this, which is even faster than what we're currently doing. So I'm also going to discuss that in a future video, so look out for that as well. But for now, let's get these things animated and let's get some circles on the screen. Well, here it is at last, folks. This is an ellipse that I've drawn with a major radius of 60 and minor radius of 50. So it is in the ratio 6:5, and as you can see, it looks quite circular on the screen. So I'm running this in an emulator, and actually in the emulator it's not quite square, so I actually had to change the shape with the video technology to make it look the way it would on a CRT, which is kind of ironic in the end. But at any rate, this is a circle, and the next thing I'm going to do is just animate the circle down the screen so we've got something nice to look at. This is just a very simple loop which just changes the center of the circle and just calls the same code over and over with different coordinates for the center. And now the other thing that I want to do, I'll just make this disappear again by drawing all the circles in black. And now I want to get some idea of how long this will take to draw an ellipse. So what I've done is I've written some code that will draw 200 ellipses on the screen, and they'll just all be next to each other. And we should be able to time that and get some idea of how long it's taking. So I'll just run that. And it's about 3 seconds to draw 200 ellipses, or thereabouts. I'm not being too precise about it. And so this means that we're getting about something like 60 ellipses a second, which is about 1 per frame, which is pretty nice. So that'll be the benchmark to beat in later videos, and I think that I'm going to be able to show you a little bit later that we can actually do much better than this. So this code is already pretty optimized, and it's probably what you would try to run if you were, say, writing a basic interpreter or something like that. But later on, you might decide you want it to be faster. You'd have to write more code to do that. And if you were writing something like a basic interpreter that was going to be running in ROM, you just wouldn't have room to do that. I think the IBM Basic doesn't actually have a circle routine in ROM. From memory, I think you have to run the Basic A from disk to get that. So maybe space is not such a big deal there, but even still, you don't want your code to be so bloated. And similarly, if you're writing a drawing program or something like that, you don't want it to take a very long time to load. And so it's rare that people go to this extent of trying to optimize and optimize and optimize. But this is something we can do in the modern era, and it's a lot of fun to see how fast we can make things go. But at any rate, that's how fast we've got it going now, and in later videos we'll try and improve on this a little bit.